We now need two services to be running for our application: the Quart web server and a Postgres database server to store our data. For this and all of my other courses, I will be focusing on developing locally using Docker, as this is the preferred development environment used by professional teams. If you haven't used Docker before, don't worry. Just follow the instructions. So let's go ahead and set up our local Docker development environment. First, you need to download the Docker desktop client for Windows or Mac, which you can find in the Docker website. Once you have Docker client running, you can check if it's properly installed by typing the following on your terminal. If you see a welcome message, everything is good to go. Let's start by creating our Dockerfile. First, create the directory where the application will live. You can create this directory inside your user's home directory. If you plan to use a directory outside of your personal folder and you are a Mac user, you will need to add it to the Docker client file sharing resources on Preferences. So let's call the directory Quart app, as this will be a boilerplate for any app. So do make dir Quart app. Navigate inside this folder with cd Quart app. Typically, an application will have different services like front-end and back-end. Since this application will be just back-end, we will create a new folder which we will call back-end service. So do make dir back-end service. Now we can create our Dockerfile inside the back-end service directory. We're going to use a multi-stage build approach, which is a Docker best practice that allows us to have different environments for development and production. Let's break down this Dockerfile stage by stage. The base stage sets up our foundational environment. We start with Ubuntu 22.04 as our base image and set Debian frontend non-interactive to prevent interactive prompts during package installation. We then install essential packages, including Python 3.10 and its development tools. Notice the ANN/REM lists at the end. This is a Docker best practice that reduces the image size by removing package lists after installation. We make Python 3.10 the default Python 3 version using update alternatives. After that, we install Poetry version 1.4.2 using the official installer script and add it to the path. We configure Poetry to not create virtual environments since we're in a container, and that would be redundant. We set up our working directory and copy just the pyproject.toml first. This is a crucial optimization. By copying only the dependency specifications first, we can cache the dependency installation layer and avoid reinstalling dependencies every time our application code changes. In our development stage, we install additional development tools like Vim and Git that we might need while debugging. We then copy our application code and install it using Poetry. We expose port 5001 and set up Hypercorn, an ASGI server, to run our application with the reload flag for development. The production stage is similar but streamlined. We copy the application code and install it, then expose the same port but run Hypercorn without the reload flag for better production performance. This multi-stage approach lets us keep our development and production environments consistent while optimizing our production image size by excluding development tools. We can use different configurations for different environments and maintain a clean separation of concerns between base requirements, development needs, and production deployment. Save the file. Now let's create a Docker Compose YAML file in our project root directory. This file will orchestrate both our application and database services. Let's examine this Docker Compose configuration. For our web service, we specify the build context as backend service, which tells Docker where to find our Dockerfile, and we target the development stage of our multi-stage Dockerfile. We map port 5001 between the container and our host machine, and mount our local directory into the container at /app, so our code changes are immediately reflected. We link the web service to the database service, which will be accessible as Postgres inside the web container, and specify that the web service depends on the database being up first. We set up environment variables that our application will need, things like database credentials and application settings. Notice we've added env for dynaconf Docker, which will tell our configuration system which environment to use. For the database service, we use the official Postgres 14 Alpine image. Alpine Linux is a lightweight distribution perfect for containers. We set it to always restart if it crashes and expose port 5432 for database connections. The environment variables here configure Postgres with the same credentials we referenced in the web service. Save the file. These two files set up a complete development environment where we can build our Quart application with a Postgres database, all containerized and ready to run. The setup follows Docker best practices like multi-stage builds, layer caching, and proper dependency management, providing us with a consistent, reproducible environment that mirrors what we might use in production.